This is Chapter 5, Database Design 1, Normalization. It's part of CIS 307 and it's part of the Iowa Community College Online Consortium, the ICCOC. The chapter begins on page 155 and introduces you. In the introduction, we talk about what normalization is doing is we need to identify the existence of potential problems, which are known as update anomalies. And we do that when we identify those potential problems. We identify them by breaking our table design down into first, second, third, or fourth normal form. This is what is referred to as normalization, as you go through and redesign those tables so that they meet one of these four normal forms. Before we can really explain first, second, third, and fourth normal form, we need to go over two things. One is functional dependence, and the other one is keys. You've heard me talk before of primary keys and foreign keys. Here we'll also be introducing another term, candidate keys, into the mix. So, to begin, on page 157, they define functional dependence. A column is functionally dependent on another column when each value in the second column is associated with exactly one value in the first column. So if we think about the Premier Products database and we think about the rep table, the question, that rep table, and it's on page 156, there's the rep table there, and you've got the rep's number, last name, first name, etc. Is the last name functionally dependent on the rep number? And the answer is yes. If you're given a value for a rep number, you will find a single valued last name that's associated with it. So the last name is functionally dependent on the rep number. Take a look at the customer table, the next one there in figure 5.1. The question is the customer name functionally dependent on the rep number? And the answer there is no. You can look down that table and you can find a particular rep number, but you're going to find a different customer name for each of those rep numbers. Thus, one rep number can be associated with multiple customer names. Take a look at the order line table. Is quoted price functionally dependent on the order number? And the answer is no. If you take a look, you'll find that an order number occurs in a row where the quoted price is, let's see, for example, 21610, the quoted price is $495, and the next one, third record, is the same order number and the quoted price is $399. So those quoted prices you need that quantity number ordered and the part number together in order for that whole thing to be functionally dependent back to the order number. The order number, the quoted price in and of itself is not functionally dependent. In other words, an order number can be associated with more than one quoted price. Sometimes a primary key is the combination of more than one things. So what is quoted price functionally dependent on? It's the concatenation of the order number and the part number. When you look at the order number and the part number together, the quoted price then becomes functionally dependent. Then we've talked about primary key in the past, and they define again, I should say, at the bottom of page 159, a primary key, being very specific this time. A column is primary key if all columns in the table are functionally dependent on that column, and if it's a concatenated key. Remember, that means that the primary key is more than one field concatenated or strung together, combination of fields. If it's a concatenated key, no other concatenation of fields or single field would fulfill the same purpose. Again, let's think about Premier Products, the database we've worked with the most. Is class the primary key for the part table? Again, you can see those tables on figure 5.1 on page 156. And no, class is not the primary key of the part table. The other fields are not functionally dependent on it. In other words, class does not uniquely identify each record in that table. Is customer number the primary key for the customer table? Yes, a customer number can only be assigned to one customer and will only appear in the customer table one time. Is the combination of order number and part number the primary key for order line? Yes, together, those two fields together uniquely identify each record. Neither one of those fields can do it on their own. Is the combination of part number and description the primary key for the part table? Well, if you take a look, this one's a little tricky because if you put the part number and the description together, they are unique. So at first you might think that would be a possible primary key. But no, while together they are unique, reality is the part number itself is unique. It identifies each record all by itself, and therefore part number is the primary key. The fact that if you concatenate it with description, it's still unique is irrelevant. Well, that brings along the next definition of a type of key. You know, we've talked about a primary key, which I just defined again. We've talked about the foreign key, and that would be a foreign key is a field or combination of fields where it is not the primary key of that table, but it is the primary key of another table. Thus, it's referred to as the foreign key because that relationship is built between those two. And now we're throwing in a new thing called candidate key. And they talk about candidate keys for the first time on the paragraph of page 161 at the top of the page outside of the blue boxes. A candidate key would be when a table has more than one field which would meet all the criteria and could possibly be a primary key. A great example of this would be if you could imagine what your database, what the student table of your college's database might look like. That student table is going to have some type of a student ID number that's been assigned to each student. It's going to have a variety of information like your first name, your last name, your middle name. Okay, but it's most likely also going to store your social security number. Your social security number uniquely identifies each student. So does student ID. So social security number is a candidate key. Student ID is a candidate key. Both of them could be the primary key. So what you want to keep in mind when you're trying to determine that is that you want to always look to see if you have more control over one of those candidates than you do the other. Your institution assigns the student ID. Therefore, you have complete control over it. The social security number is out of your control. It is assigned by another agency. Theoretically, it is unique. There have been situations, especially people who received social security numbers back before computers were so prevalent, and it was done in a much little more labor-intensive process. I once knew somebody in my life. I went to junior high with him, and he had two social security numbers. His parents were divorced. His mother had went and gotten him one, and his father had went and gotten him one. Again, it was before computers were they weren't on everybody's desk. I'm not so ancient that they weren't invented yet, but it was, the early 80s that it happened. And so he actually, as an adult, had to go to the Social Security Administration and explain what happened, and he had to get one of those social security numbers deactivated. So again, it's not within your control. So as the database administrator, you always want to pick the one that you have more control over. Okay, so with those definitions in mind, that brings us to the bottom of page 161 where they define first normal form. And they define it as a table is in first normal form when it contains no repeating groups. So let's take a look at figure 5.5 there on page 161. When I look at something like this and they call it a table, I look at it myself and I think of an Excel spreadsheet. And I think of it that way because of that repeating group there. When you take a look at there's the unnormalized data. You've got that part number multiple times to the same order, and of course you have the number of ordered of each of the part numbers to the same order. If you took a look at the next figure, 5.6, on the next page 162, this has the data converted the table to first normal form. Notice that if you take a look at the two that are highlighted a darker blue on order number 21617, they're trying to show you there that part BV06 and part CD52 are both present for that order. They have another situation up in rows 2 and 3 where both part DR93 and part DW11 are both present for order 21610. The primary key to the unnormalized orders table was the order number in figure 5.5. But once it's been normalized, it's now the combination of order number and part number. So you can think of it this way. If we were to look at the notation for the data in figure 5.5, we'd have an orders table with order number as the primary key and the order date, and then for the next part another set of data because it was multi-valued with the part number and the number ordered. But if you took a look at once it's hit first normal form, we now have that concatenated key. So all the data has the same rank, and it's the combination of order number and part number together that uniquely identify each record. So now the data has hit first normal form. This is very basic data normalization. It just comes down to a field cannot contain multiple repeating data like that, like it did in figure 5.5. But just because the table gets to first normal form doesn't mean that all of its problems are gone. If you take a look at figure 5.7, figure 5.7 on page 163 is a sample orders table, and it is in first normal form. The notation for this shows that the primary key is order number and part number together. But if you take a look, you'll notice that the description is being stored in here. Notice that description is tied only to part number, and order date is tied only to order number. I think I'm getting ahead of myself. Table is in second normal form when it's in first normal form, and it has no non-key columns dependent on only part of the primary key. Now, if a table has a single column primary key, in other words, the customer table has a primary key of customer number, one column, one field, it is in at least second normal form. But when you have that concatenated key, you're not as sure that it's in second normal form. So we have to now look for that we have dependencies on non-key columns. And if you take a look at figure 5-7, that's the one I guess I already directed you to, the description is dependent on the part number. The order date is dependent on the order number. Neither the order date nor the description are part of my primary key, so those are non-key columns, but yet they're dependent on only part of the primary key. They're not dependent on the combination of order number and part number together, but instead they're dependent on only part of the primary key. In figure 5-7, a change in the description would have to be made to multiple rows. In other words, if they've highlighted in darker blue the two rows where the order was for a gas range. If tomorrow they changed the description of that from gas range to gas range XL, you would actually have to go into each record that referred to gas range and change it to gas range XL. That could be very time consuming to update. And then it can lead to inconsistent data because you typed it in so many different times and had to go through and edit it. If one time you did space XL, another time you just did gas range XL without a space, etc. Now you don't even have like descriptions. I can tell you when I was a consultant, I worked with so many companies in town that had problems in their customer field because they'd have John Deere, they'd have Deere and Company, they'd have Deere Davenport Works, they'd have all over the place. It's just inconsistent data. High V with a dash, high V with a space, high V as one word. As a result, when you're trying to just get a list of all of them and you just unique that column, you still end up with high V listed 3 and 4 and 5 times because of different spellings of it. Another problem is that if you were to if you had a new part that you wanted to start selling, you would have no place to put that information because you've stored it in the orders table, the description, so you can't have a record of the description until you've placed an order. And the same is true with a deletion. If for some reason you did have to get rid of a row out of that table, if you removed that row and it was the only order for that particular part, then again, you'd have no record of the description. So the additions and the deletions are kind of the same, similar problem. So again, when we back it up a minute and we take a look at the data notation in figure 5.7, that is the table that's met first normal form, but it hasn't met second normal form. So our primary key is the combination of order number and part number, but order date is dependent on order number. Description is dependent on part number. Therefore, we have fields that are dependent on only part of the primary key. When we normalize this data, and that's what's on page 165 in figure 5.9, we find that we actually have to split it into 3 tables, and we determine that by actually mapping out or diagramming the dependencies. That's what they're showing you in figure 5.8. And once you've mapped out those dependencies and determined where they are, you can make this data meet second normal form by breaking it down into 3 tables. So we'd actually have an orders table where the order number and the order date are the only fields in there. A part table that contains the part number and the description, and then that order line or order detail table that actually shows the order number, the part number, the number ordered, and the quoted price. So if it has to do with the order, it's in this table. If it has to do with the part, it's in this table. If it has to do with the order of that part, then it would be in this table down here. This now meets second normal form. But what about those times when you want to see it all at once? You have somebody who wants to see all of that data. That's when we create a view. Okay, now we move into third normal form. A table is in third normal form when it's in second normal form and only determinants it contains are candidate keys. Okay, well there's another new word, determinant. A determinant is any column or columns that determine another column. It's probably best to understand this by actually taking a look at an example. If we take a look at figure 5.10, we'll see a sample customer table. This table is currently in second normal form. It has a single field of customer number as its primary key, and if you remember, anytime your primary key is one field only, that table is in at least second normal form. However, they are also storing information about the rep number inside of this table. So the rep's first name and last name are also being stored in the table. They are determined by the rep number, but rep number is not any part of the primary key. So that means that it's a determinant. Remember, a determinant again is any column that determines another column. So the rep number determines the rep's first name and last name. This has same problems that we had before. We've got time-consuming updates because that rep's last and first name are repeated multiple times. Every time they represent another customer, they are repeated in this table. So we'd have to, if a rep got married or changed their name, we would have to take a lot of time to go through multiple records to change their data. As a result, we end up with inconsistent data because we didn't perhaps spell it exactly the same. Even something as that is you can't even see, like Smith with a space on the end. You may not even realize it, but then you do something just as simple as a mailing label or a mail merge letter, and you have a mess simply because, again, of that inconsistency. Until the rep number actually finds a client, a customer, and makes a sale, we don't have any record of who that particular rep is. And if a particular customer is deleted or archived from the table, then it's possible that all data telling us who that particular rep is deleted from the table. So again, it's these same problems with updates, inconsistencies, and additions and deletions. So when we take a look at it, and we look at the actual dependencies, and that's what they're doing in figure 511. They're trying to map out and show you that the customer name number determines the customer name, determines the balance, etc., but that the rep number determines those two fields. If we actually took a look at the notation for the figure 510, we'd have a customer table with a customer number as the primary key. But when we actually make this data meet third normal form, that's figure 512 on page 168, we again have to split the data into multiple tables, taking those last three fields, that number, last name, and first name, out of that table and putting it in its own table so that we can actually create a relationship here between the two rep number fields. Remember, I'm just trying to bring this back full circle. Here rep number is the primary key. Here rep number is a foreign key. So ultimately we would be relating these two tables together through that common field. So again, we have to break it down. And again, if somebody wants to see it all at once, that's why we create a view. Before we actually go into fourth normal form, we need to talk for a minute about what can happen if you break this down into multiple tables erroneously, or what the author calls incorrect decompositions. One big problem that you're going to have with incorrect decompositions is data redundancy. And they give you an example of that in figure 513 on page 170. Here, this is an incorrect decomposition of the customer table. And if you take a look at figure 514, it's another different way, incorrect decomposition of the customer table. The second one on page 171 has a great example of data redundancy, because here you'll notice that the rep number is in the rep table is split out correctly, rep number, last name, first name, but the rep number isn't what's repeated over in the customer table to draw the relationship. They've got the last name and the first name. So we still have, if you take a look, Juan Perez again and again and again inside of the customer table. We'd rather have that number. You're going to have something again and again, but the number would be the better choice. So that's giving you a lot of data redundancy. Same thing in the other one, or similar. In the one on the left-hand page, they're not even pulling the rep number over into the rep table. They're pulling the customer number over. So by pulling the customer number over, you're having to repeat the rep names again and again and again, just in a little abbreviated table over there. Again, data inconsistencies and updating nightmares. So the other big problem or thing to keep in mind is that you always want to link the primary key to the foreign key, not just dependent data. So that's what I was referring to on page 171, where they're trying to create the relationship between the rep's last name and first name, like they're making that the primary key. Couldn't I hire two Joe Smiths? Sure I could. I need to give them each a number so that I can uniquely identify them. That's that rep number that becomes my primary key that I need to then bring over into the customer table as the foreign key. So again, these are just some bad examples of what they call decomposition, or just of taking that data set and breaking it down into multiple tables. Then they're ready to discuss fourth normal form. A table is in fourth normal form when it's in third normal form and there are no multi-value dependencies. So another new word, multi-value dependency. When the data in the first column is related to data in the second column, and it's related to data in the third column, but its relationship to data in the third column is independent of its relationship to data in the second column. And they really do a great example here on page 515. In the top picture, what they're trying to show is, imagine that you've been tasked with keeping track of some various things of faculty members, and you're supposed to keep track of students that they advise, and you're also supposed to keep track of committees that they serve on. These are two completely unrelated problems, yet if you used a spreadsheet to track it, you might come up with a design similar to that first picture in figure 515, where you have one faculty number perhaps their name is in another column somewhere, but then you would have lists of students who they advise, and somewhere else you would have some type of committee code for the committees that they serve on. What students they advise and what committee they serve on are independent of each other. So you're trying to use one table to store things that are not dependent. In other words, the students they advise and the committee they serve on, while they each have a relationship to the faculty member, they do not have any type of relationship to each other. So no type of dependency on each other. So this is a multi-valued dependency if you try to put that in one table. You can take that data and you can break it out in the second picture there. You've actually broken it all the way out to third normal form. It has no repeating groups. It has no column dependent on only a portion of the primary key. It has no, I think I have a slide on this. There we go. No determinants exist that are not candidate keys. So in figure 515, the second half, they've taken that bad example of a table and put it into a table that actually meets first, second, and third normal form. But the question is, does it meet fourth normal form? So we kind of take a look at it and we realize, well, there's still some update problems. If a faculty member decided to stop serving, for example, on the CUR committee, that's repeated in there a number of times, well, we'd have to, if we deleted those rows, I guess that would delete everything for faculty number 456 because he's only on that one committee. Or if a faculty member decided that first faculty member 123 decided to stop serving on the PER committee, personnel committee, you'd have to delete the third row, you'd have to delete the sixth row, because they're both telling you the committee, they're just for each one is for a different student. So we still have update problems, we still have addition and deletion problems, and that's usually a pretty good sign that you're not making it all the way to fourth normal form. If you take a look at the picture on page 176, in this case, the two types of data are not related to each other. What committee the faculty member serves on, committee or committees, and what students the faculty member advises are two completely separate issues. And you may have been wondering that all along. Why are you even trying to put this in the same table? You don't put that type of data in the same table. It needs to be split out into two different tables. So in this last picture, you see figure 516, fac student, tells you the faculty number and the student number of who they advise. And then the one on the right-hand side, FAC committee, is the faculty number and the committee that they serve on, committee or committees. Now we've hit conversion to fourth normal form. If you took a look at the notation for it, in figure 515, we had one table called faculty, and that table had 3 fields in it. All 3 together made the primary key, the faculty number, the student number, and the committee code. The problem is that this data was dependent on faculty number, but it was independent data. So by hitting that fourth normal form, we actually have to break it out into two separate tables. So we have a faculty student table with the faculty number and the faculty name or student name, and then a faculty committee table with the faculty number and the committee code. Again, if you want to see it all at once, create a view. So the way this applies just to your database design, which is the last thing that they talk about there on page 177, 178, is that as you break your tables out, as you're designing them, I've always said to people for years and years, a good database design starts on paper. You don't start off and open up your Access or your Oracle or whatever program you're using to actually design it in. You start off on paper. You lay it out. You plan it. You have a wall of sticky notes as you move things around, and you actually get that table design down. And one of the steps of breaking out that table design is data normalization. This concludes the Chapter 5 lecture.